Winning a race demands the right car with the right engine under the hood. That's the concept TE has applied to developing its brand new line of 25G active optic interconnects for communication systems. These new high-speed products transfer data at 25 gigabits per second, while consuming about half the power of similar products. But what's the engine inside that's driving this performance? TE Coolbit Optical engines. These tiny engines convert data from electrical signals to optical signals, enabling communication systems to have higher density, higher speed, and greater energy efficiency. With parallel channels, you can get up to 300 gigabits per second of bidirectional data for a 12-channel device, or even more. This is the equivalent to downloading 100 DVDs in 5 seconds. Let's take a quick tour of TE's facility in Jarfalla, Sweden, and see how these engines are made.
Welcome to TE's Jarfalla fabrication facility in Stockholm, Sweden. This is where we manufacture our active optics in a fully vertically integrated capacity. I'm Dr. Ivar Hamburg, and I'm responsible for the manufacturing process. I'd like to share with you how we make these state-of-the-art devices.
Coolbit optical engines are developed and produced in an automated wafer scale assembly line at the Jarfalla Fabrication Area. This production facility is about 2 orders of magnitude cleaner than a surgical lab. Tiny products must be protected from the tiniest impurities at all times. TE leaves nothing to fate. TE controls the entire manufacturing process, research to release. And Coolbit is our latest creation, from start to finish. TE's Coolbit engines are composed of 4 subcomponents, or semiconductor chips, mounted on a subassembly. The core structure of the device is a laser diode. At its heart is an epitaxially grown stack of dielectric layers and quantum welds. These layers are grown at high temperatures in this reactor, layer by layer, on an atomic scale. There are several hundred partial layers, grown with high precision and perfect crystallinity. The laser diode structure is called a VCSEL, or vertical cavity surface emitting laser. After this epitaxy structure has been grown, we take the wafer through a series of process steps in the wafer fabrication area to build up the complete laser chip. Semiconductor production involves 3 basic steps. 1. Deposition. 2. Photomasking. And 3. Etching. This sequence is repeated several times to build up the structure on the wafer. Here we see a deposition step. The wafers are loaded into a plasma deposition system. A layer of dielectric material, such as silicon nitride, is deposited. Photolithography defines the patterns on the wafers. A photosensitive polymer resist is spin-coated on top of each wafer. A pattern is then exposed with the help of an aligner. The result is a patterned polymer mask on top of the wafer. This mask protects certain areas in the subsequent etching step. Several etching methods are used: plasma etching, wet etching, and ion milling. Here we look at ion milling. A high-voltage accelerated argon ion beam is focused on the patterned wafer. The beam gently removes material from open areas in the mask. This process is very accurate, very clean, and incredibly precise. Deposition, photomasking, and etching are repeated several times with different materials and with different photomasks. That creates several patterned layers on top of the wafer, defining all the necessary features of the semiconductor chip. The wafer holds thousands of tiny components. Every chip is automatically tested in a wafer prober and is actively stress tested to verify performance and ensure reliability. Then the wafer is diced into single chips. The individual chips are selected and picked into a tray. They are now made ready to be used for the assembly of the Coolbit engine. Pin detectors are also fabricated in a similar way to the laser diodes. These 2 components handle receive and send functions of the finished engine. The laser diode and its driver IC, and the pin detector and its amplifier IC are all mounted onto each site on a patterned glass wafer to make a dense, compact transceiver subassembly. These 4 different components are placed on the large substrate through automated flip chip assembly. The process is fast, precise, very reliable, and fully automatic. The finished wafer holds hundreds of these Coolbit engines. The units can be made for different product versions. After the whole wafer is populated with components, it is divided into small individual units for testing. The Coolbit optical engine is complete. This little device has the capability of both sending and receiving data at data rates of 25 gigabits per second, giving a transfer rate of 300 gigabits per engine or more. It's simply a faster engine for a world that has an ever-increasing need for speed.
Well, that about wraps up our tour. As you can see, our manufacturing is fully vertically integrated. This ensures that you get the best possible product. The IT world is pushing for bandwidth growth in data centers all around the world. Our Coolbit optical engine is one of the ways that TE is helping the IT industry to meet this ever-increasing demand. These tiny engines allow our active optics products to drive higher density, greater speed, and lower power consumption, allowing you to build more efficient, cooler communication systems. The Coolbit engine is ready for the next generation of data centers. Are you?